Hi, I'm Farhana. Thank you for joining me in this lesson. We'll be doing some work on trigonometry rules, and specifically, we're focusing on three-dimensional trigonometry. Let's have a look at our concept map first. Okay, so far we've covered solving non-right angle triangles in the sessions before this. We've covered sine rule, cos rule, and area rule, and we've also covered the proofs and applications. This time we're focusing on 3D problems. Before we begin, let's do a quick recap of all the rules and when to use each rule. So, let's begin with the sine rule. Okay, what is the sine rule? The sine rule is sine A over A equals sine B over B equals sine C over C. And we have the reciprocal versions, which we use when we're looking for a side, and it's A over sine A, B over sine B, C over sine C. And can you remember when we can use the sine rule? We're allowed to use the sine rule when we have, that's correct, when we have one full pair of sides and angles. Okay, so if we look at this diagram here, let me just grab my pen quickly. Okay, so you must be given A and angle A and the side across it. Any full pair like that where you have one angle and its matching side, then we can use sine rule. Okay, so basically we can use sine rule when we have angle, angle, side, or side, side, angle, and remember in this case, it's not the including angle. Okay, we have the sine rule, the ambiguous case. Can you remember when we have the ambiguous case? It's when we have two sides and an angle, but the side given opposite the angle is the shorter of the two sides. So in this case, 6 is the shorter side. So in this case, 6 is less than 10. So we will have the ambiguous case. And remember, we can draw two different triangles for this with the same information. Okay, and our next rule, area rule, this is an easy one. Remember, we're looking for a kind of a V pattern when we're doing area rule. So we need to have half AB sine C, half BC sine A, and half AC sine B. Okay, and you use area rule when you have side, angle, side. So basically, you can use it when you have AC and the sine of B. So we're looking for the V pattern. Okay, and when do you use the cosine rule? When you have two sides and included angle. So what is the cosine rule? A squared plus B squared minus 2BC cos A. B squared is equal to A squared plus C squared minus 2AC cos B. And can you remember the last version? C squared is equal to A squared plus B squared minus 2AB cos C. Okay, and remember, we can also use the cosine rule when we want to find an angle. All we do is just rearrange the equations we had in the last slide, and then we can find our angles, A, B, and C, using this version of the cosine rule. In this case, remember, we have to be given the three sides to find one of the angles. Okay, and then when we're deciding which rule to use, hopefully you can remember this. We've been through this in the previous sessions. Okay, if it's a right angle triangle, then we ask if it involves angles, and if it does, then we use the trig ratios, sine, cos, and tan to solve it. If it involves no angles, it only has sides, then obviously we're going to use theorem of Pythagoras. Okay, if it's not right angle triangles, then we've got to look at to see if we have one full pair, an angle and its matching side, and if we have the angle and its matching side, then we can use sine rule. Okay, and if we don't have a matching pair, a matching pair of an angle and its side, then we've got to use cos rule. And remember again, sine rule is used when we have angle, angle, side, or side, side, and not included angle. And cos rule is used when we have side, angle, side, or side, side, side. And remember, in cos rule, we're looking for that V pattern. Okay, hopefully you remember all those rules that we've done before and when to apply them. Let's look at our first three-dimensional drawing in this example. So we have a cuboid here that's drawn with its measurements as shown. calculate the length of BD. The second question, calculate the angle between BH and the base of the cuboid. Now, before we begin, we need to understand the different planes that are present in this figure, because it will help us understand which angles are right angled and which are not. Okay, so if we look at our cuboid, you'll notice as it stands, we have a vertical plane in front, we have another vertical plane at the back, we have this plane, and this is a horizontal plane. The top and the bottom are both horizontal planes, and then we have two more planes. That's the one on the right, and this one here at the back. Now notice something, a lot of the diagrams that you will see in 3D trigonometry will kind of remind you of a corner of a room. So if you look at this room that we have here, we have that line and that corner here. Okay, so this wall here, if you remember it as looking like a wall, is always right angled, because this plane, the plane where the wall is sitting on, is perpendicular also to the plane of the floor. And similarly, this angle here will be 90 degrees. Okay, so picturing a corner of a room kind of does help us when we're doing 3D trigonometry, as you will see a little bit later. Okay, so now they've asked us to calculate the length of BD. And BD is this line sitting on the base of this cuboid here. And because it's lying on the base, we realize that this angle here is 90. And because this angle here is 90, we actually have a right angle triangle. And because we have a right angle triangle in triangle BAD, we can then use grade 9 theorem of Pythagoras to solve it. So it becomes pretty simple from here on. And remember, here's our right angle triangle, and we've got this side is 7, and this side here is the same as this, so they both are 4 centimeters, and there's our 4 centimeters here. So now we have to solve this using Pythagoras. This is pretty simple, grade 9 work. You'll say BD squared is equal to AB squared plus AD squared, and that's going to equal to 4 squared plus 7 squared. And your answer is 65, but remember we're looking for BD, so it's the square root of 65. Okay, that should have been simple enough. Let's go to our next question. Now they've asked us to find the angle between BH, which is this line here, okay, and the base of the cuboid. So they want the angle between that and that. Now remember earlier we found this BD to be square root of 65. Okay, so because that's square root of 65, and this is a vertical plane, it's perpendicular to the horizontal plane or the floor of the cuboid. So basically now we have a new right angle triangle in BDH, and we want to solve this, which is the hypotenuse. So if we redraw this, and it does help to redraw the triangle separately with the information you want, just so you can make sure you understand where the right angle triangles are. Here's a drawing. Okay, so BD is root of 65, and here's our right angle triangle, and DH is 6 centimeters. And again, the calculation is easy, just to visualize where the triangle is sitting. I think that's the part that requires a bit of skill and getting used to. And now we just do Pythagoras again. Sorry, now we want to find the angle, apologies. So we've got to use, we have the opposite and the adjacent, so we're going to be using tan of theta, because tan is the ratio that has opposite and adjacent, so it's going to be 6 over 65. Okay, and then you're going to use your calculator to say shift tan, 6 of 65, and you've done this a lot in grade 10 and 11, so you know how to find the angle then, and so you'll get the angle to be equal to 36.7 degrees. So it means that this angle here is now 36.7 degrees. Okay, we're going for a quick break. I'll see you after the break.